Welcome to Chapter 18, and we will continue on with nucleophilic acyl, and one of these is addition. This is the mechanism versus substitution. And substitution is when you have carboxylic acid derivatives. So there's a leaving group. Addition is when you have aldehydes and ketones. And we really focus on this is the mechanism, the reaction mechanism, which you're required to know how to draw the intermediates. They go through the tetrahedral intermediate. And then you need to know the different reagents, starting materials, and products. So starting materials, reagents, and products. This is the functional group transformations. All right, so here, what is the missing reagent? So you're going from a carboxylic acid to an acid chloride. And you don't actually need to draw the mechanism here, you just got to fill in the reagent. And that is thionyl chloride. This is called thionyl chloride. And what does that Lewis structure look like? What's happening here is the OH is not a great leaving group. So thionyl chloride makes a derivative such as this. And then the Cl. So what happens is that oxygen sulfur is, now this is a great leaving group. And the 1Cl is now able to do the substitution, nucleophilic acyl substitution, and replace this OH, substitute with the OH with one of these Cl's. And this is an acid chloride, so you need to know those functional groups. This was a slide that we left off with, and you can go and look at the previous lecture. Okay, so this is the mechanism we're going to talk about here. This is an aldehyde, and we have some acid catalyst, and we have a weak nucleophile. And since we have a weak nucleophile, we need the acid catalyst for the aldehyde carbonyl. And we're going to, step one, you need to know this mechanism. You want to protonate the carbonyl oxygen. Second, the weak nucleophile will add to make the tetrahedral intermediate. And then the third, you'll get deprotonation to give you the hemiacetal. That's the halfway part, hemiacetal. It's a new functional group. You need to recognize the hemiacetal. Then the fourth thing, you're going to get protonation again of the OH, because you want to make this to make OH a good leaving group. Actually, yeah. And then the fifth, reform the carbonyl as water leaves. Then you have the weak nucleophile adds again. form the tetrahedral intermediate. And let's see, when that happens, that leaves, adds again, and this should form, you'll have to have, I think, another deprotonation step to give you the acetal. And so you need to know that's a new functional group as well. So you're going to see the hemiacetal and the acetal. Okay, so you can get those informations down here. Let's see if we can. So the first step, we're going to protonate the carbonyl. You need to be able to show curved arrows to show these mechanisms. So here is the lone pairs, and there's your positive charge on the oxygen, and we've protonated the carbonyl oxygen. This has made this more electrophilic, activates that carbonyl, and now you have the weak nucleophile adds, and this is going to give you a tetrahedral intermediate. Four things. And then deprotonation to form the hemiacetal. So here you have acid catalyst. Here it's deprotonated to make water. And then this water can turn around and deprotonate to give you the hemiacetal. So there's your hemiacetal. This is what you would see as a hemiacetal because you wouldn't have your hydrogen in there. So that's the hemiacetal. This carbon is bonded to an OH, and it's also bonded to an O carbon. So that carbon has two oxygens there, hemiacetal. Okay, that's the halfway. At this point, let me erase these steps here so we can have some room. All right, so the next step is protonation of the OH to make a good leaving group. So this OH is still an acid, H3O plus, so this is going to get protonated. Make water. Now that's a good leaving group. And we're going to reform the carbonyl as water leaves. So here's fifth step. So these electrons will go here to form a carbonyl and push the water out. And you see how that's kind of like this one here, the very first one where the oxygen is protonated, that activates this carbonyl carbon. And make sure you have your lone pairs here. And so then the next step, so we've done this, reform the carbonyl as water leaves. So we reform the carbonyl, water is left. Now the nucleophile, the weak nucleophile will add again because the CH3OH, that's your solvent, will add to this activated carbonyl electrophile. And it's been activated. We're going to form the tetrahedral intermediate. Here's our formal charge. So we form the tetrahedral intermediate. That carbon has a hydrogen there, so you have a hydrogen there. There's your four things. And then you're going to get protonation, deprotonation of the acetal to form the acetal. So we have the water that will deprotonate this to give it a neutral compound. And so there's your OCH3, and then you have OCH3. And this is your acetal. So an acetal is a carbon that's bonded to an O carbon, O carbon. So that's a new functional group. That's an acetal. So an acetyl, acetal, you can hear that interchangeably. The Al and the hemiacetal, hemi has halfway there, see the OCH3. This is a protecting group for the aldehyde. So this is we started with an aldehyde is our starting material. And just like we did protecting groups with silyl ethers for an alcohol, this is a protecting group, an acetal is a protecting group for an aldehyde. And so that means an acid and water, that's all you need. You can actually regenerate your aldehyde. And so this is chapter 18. We're going to be talking about reactions of the carbonyl group, aldehydes and ketones. A lot of this will be slides I've already talked about, so I will rapidly go through this. We've talked about this uncrowded sp2 carbon and how aldehydes are less crowded than the ketones. We've talked about the steric hindrance and how aldehydes are less sterically hindered than ketones, so they're going to be about 10,000 times faster reacting than the ketone. How to name these compounds. It has a higher priority. When you have a higher priority than like alcohols and stuff, you have to, when you do the longest chain, you have to contain the CHO group, and you're going to have to give its lowest number. The CHO group, the aldehyde, will always be number one because of the hydrogen. It will have to be at the very end of the chain. And so, and you notice that al is at the end of the name. So here we have 1, 2, 3, 4, 5, 5. So that would be pentane, but we're going to drop the E and add Al, so pentanal. And then we have this 3-methyl substituent. You don't have to give a number for the aldehyde because everybody knows that it has to be at number 1. These are also common names if you need to look them up. I'll usually talk about formaldehyde or acetaldehyde. You might hear me use those two. Or benzaldehyde. We're going to be talking in the next couple weeks about reactivity at the alpha and the beta. So this is the alpha. It's the first. These are Greek letters that come from the carbonyl. And this is your beta. Sometimes you do gamma. You really don't go past. Here we'll just talk about the alpha and beta carbon in some of the future chemistries. So in ketones, the suffix is -one for ketone, and you do have to give a number because the ketone can be anywhere in the chain. It does have a higher priority, just like the aldehyde, so it has to give the lowest number. And it has to be included in the chain. So here, 1, 2, 3, 4, the ketone needs to be on the 2. This is a common name. This is a common name, acetone. A lot of these are common names. So here, 1, 2, 3, or 1, 2, 3, 1, 2, 3, 4, 5. We'll do 2 because it also picks up the methyl group is a low number. So it's always about the combination. So 2-methyl, pentan, 3, and you got to say where the ketone is, 3-one. This one, it's metabromo because it's a 1,3 combination, acetophenone. This is the formal group, acetyl group, benzoyl, that's a new one for you, and you have seen the benzyl. Um, you don't have to name these. Don't worry about these so much. Well, I don't know, you might. Let's see. Um, Ene means you got it. Yeah, you would need to. What they're trying to show you here is that the lower numbers in the chain need, because you got to have the double bond in the longest chain, but your lower number needs to be with the carbonyl because it has a higher priority. Yeah, that would be important. And carbonyls are going to have a higher priority over alcohols. Alcohols have a higher priority over alkenes and alkynes. So you might want to look at, for nomenclature, the priority as you get more functional groups. So the carbonyls are going to be higher than alcohols, and alcohols are higher than alkenes and alkynes. Alkenes and alkynes are higher than halides. But anyway, so here we have 1, 2, 3, 4, 5. Priority means you've got to give it the lowest number. So we got it, and you have to include it in the chain, the longest chain. So this is 5-pentan. So here you have to go through the double bond, 3-ene, so it's on 3 carbon, and then the ketone -2-one, and then we have a 4-methyl. What about intermolecular forces? Alcohols are hydrogen bonding, so they're going to have higher boiling points, 118. Aldehydes are dipole-dipole, so that's going to come second, and these are van der Waals. It's going to have the lowest. I basically, you can go back and look through these where you would find them on NMR. These are just some of your reading. You can read about interesting ketones and aldehydes. Vanillin is an aldehyde. A lot of your nice smelling compounds and strong odors are aldehydes and ketones. Cinnamaldehyde is an aldehyde. You can see the aldehyde here. Steroids with carbonyls. I think we've showed you some of these. Prednisone has a ketone, lots of ketones. Cortisone has some ketones. So how do we, well, this is review. How do we synthesize aldehydes? PCC from the primary alcohol will stop. It's a mild oxidizing agent. We'll stop at the aldehyde. Dibal H, it does reduce esters. And if you remember, I said, oh, in that one slide, it doesn't reduce esters. It does. And it reduces acid chlorides. These are dibal. You can use dibal for both of these. And when you use any kind of aluminum, you have to follow it up with water. And you have to separate 1 and 2 because you can't put aluminum in water. You'll have fire. These stops at the aldehyde. These are reductions. Okay, these are reductions. We're adding a hydride here to the carbon. Oxidation, we're increasing the carbon-oxygen count. And then this is the alkyne. Hydroboration of aldehyde has to be the diisolamyl boron with it makes a, remember the enol, and then it tautomerizes to the aldehyde. So those are 4 ways to make aldehyde. Ketones, how you make ketones, you can use PCC on a secondary alcohol or a Jones reagent, which is the chromium and the chromate. And usually use sulfuric acid with the chromium, the Jones reagent. You stop oxidation at the ketone with secondary alcohol, so it doesn't matter. If you have an acid chloride and you use the cuprate, remember the cuprate delivers one of the R's. There's the R prime. That'll make a ketone. If you use the Grignard, remember the Grignard or the organolithium, that's going to make a tertiary alcohol because the ketone is going to be more reactive. Acid chloride with aluminum trichloride, this is the Friedel-Crafts. acylation. So you remember that forms this electrophile, and then you get the sigma complex. Rearomatization. Here, alkynes, we do this with mercury sulfate and sulfuric acid. We make the enol, and then the enol will tautomerize. So the enol is on this carbon now, and yeah, makes a ketone. So those are 4 ways to make ketones. All right, so oxidative cleavage of alkenes also makes ketones and aldehydes. You remember ozone, and then I usually use DMS. That's oxidative cleavage. This is the reaction. So now we're going to talk about when the aldehydes and the ketones are our starting materials. Okay, so this is our starting material. The nucleophile adds to the carbonyl to form a tetrahedral intermediate. That's nucleophilic addition. The nucleophile adds. And then you quench it with water. Because you do not have a leaving group. So whether R prime is a H or a carbon, and then you've added the nucleophile. This is nucleophilic, acyl, because the acyl group is a carbonyl, and that's addition. So you're just adding the nucleophile. Substitution, we would have to have a leaving group. We're just talking about aldehydes and ketones. We will be talking about enolates in the future. This is actually a more acidic proton. You're going to find that this proton pKa is about 20, so you can make an enolate. And this is an enolate, but we're not going to talk about that until later on, and that's the alpha carbon. So nucleophilic addition is what we're going to be focusing on for this chapter. And like I said, you need to know this mechanism. The nucleophile adds, you see you have 2 curved arrows. You need to show your tetrahedral intermediate. And then you need to do the protonation step to give you your addition product. This is an acid catalyzed nucleophilic addition when you have a weak nucleophile. And that's what I started this chapter with methanol. Methanol is a weak nucleophile, so you're going to have to add some acid. You can do H3O+. You'll also see tosic acid, TSOH. What is that? That's paratoluene sulfonic acid. It's actually my favorite acid. All right. So what is tosic acid? It is a solid, a nice little white solid, and it's an organic acid. But this is its structure, OH. It is this H that's acidic, and it's an organic acid, so you can put it in organic solvents. So a lot of like H3O+, you also have water. It's very important to be able to have an acidic proton that is in organic solvents, but it delivers the proton, and that's the first step you're going to have to do is protonate the carbonyl oxygen. And the reason why you got to do that is you got to make that electrophile. You see the double-headed resonance arrows here? That activates the electrophile. It makes it a strong electrophile, which you need when you have a weak nucleophile. And now the nucleophile, which is typically going to be methanol, you'll see, or some kind of alcohol, can add to this carbon. And then, of course, you deprotonate, and you're going to find that this is called a hemiacetal, which is a new functional group. And so they're just showing you that once you protonate this in the carbonyl, it's much more electrophilic and more susceptible to an attack by a weak nucleophile. And so when you have really strong nucleophiles, you don't need any acid catalyst, okay? Um, so you'll just get formation addition. So something like this, an amine is a weak. How do you know it's a weak nucleophile? There's no negative charge, okay? Now, so you would need some acid catalyst on weak. So even though this is not showing that, I do expect you to know that because you would call that weak. And then you could say, okay, now it's ready for activation of the nucleophile. This is your, and then this is your tetrahedral intermediate. In this case, it's also your, well, it's not your product at this point. See, another reason you're going to need another acid because OH is a bad leaving group, you're going to have to protonate that. And so this is giving you some kind of shorthand version of this mechanism that's not, it's leaving out the acid, which will not work without the acid. Then you get the nitrogen reforms a double bond, just like the carbonyl. And now you get a double bond nitrogen. Nitrogen and oxygen are very similar, but this is a new functional group called an amine. All right, so let's look at ketones. These are different reagents. If you use sodium borohydride or lithium aluminum hydride, this is your nucleophile. It's a strong nucleophile. Look at the negative charge, and you get an alcohol. The Grignards, so if you add like any kind of CH3 lithium, that is also a strong nucleophile. So you're going to add to the carbonyl to add the R group, and you're going to get a tertiary alcohol. Sodium cyanide, because this is a positive, this gives you a negative cyanide, strong nucleophile, cyanohydrin. We're going to be talking about this is called the Wittig. We'll talk about that in this chapter. Notice you got to have, if you're going to add a weak, this is weak, RNH2, okay, you're going to have some mild acid. So in that case, you want to do H3O plus. These you're going to have to protonate the carbonyl oxygen first because you have a weak nucleophile. And they're just showing you this is only one R group on the nitrogen. This is two. Okay, so the same thing. You do make something a little bit different, imine and enamine. So we'll learn those new functional groups in this chapter. This is kind of a summary of what's coming. I did start out with the alcohol and the acid, and I showed you the mechanism. You see that it makes a hemiacetal, and then it goes on for another 3 steps of reactions to make the acetal. You will be expected to be able to draw this mechanism, and I did show that details the very first slide. All right, so you got to look at the functional group transformation here and say this is an ester, and the ester became a ketone. And you added a methyl group here. See the methyl? This is what was added. So this is substitution, and it's nucleophilic acyl substitution, and we're substituting the OCH3 into a CH3. And so what does that? Now keep in mind, with esters, this is going to go to the tertiary alcohol. It's going to add twice. So that's not going to be, sodium borohydride would make the aldehyde because it would add H minus. Actually, it won't add. Esters, no reaction. This is too weak. This is a mild reducing agent. It does not undergo reduction. Esters, no reduction. You'd have to have dibal will make the aldehyde here. Yes, that would. This is the cuprate. This is going to deliver the CH3. So cuprates are like those R2 cuprolithiums. These are mild and they will add. So D is your answer. Okay, so nucleophilic addition of a hydride, sodium borohydride, lithium aluminum hydride is a source of hydride, and an aldehyde is going to, you see here, either one will work and you will make the primary alcohol. Here, the Grignards are going to add, and I've already gone through these, so I'm not going to, I'll just kind of go through them quickly. The organolithium here you see is going to add to the carbonyl, and it's a strong nucleophile. Make your tetrahedral intermediate, and then you protonate to make a secondary alcohol. Here we have a strong nucleophile because sodium is a positive charge, and that's going to make a cyanohydrin. So you can see that here with this compound here. Nucleophilic, and that's the mechanism. You see your tetrahedral intermediate, and then it gets protonated. Cyanohydrins can be converted into the carbonyl upon heating and water. Well, okay, but I think we're not going to worry about this one. Here, we'll talk about nitriles. We'll do all the different nitrile reactions. But what's nice about a cyanohydrin, the carbonyl or the nitrile, if you add it in acid and heat, you can convert it to carboxylic acid. So the nitrile is a precursor to the carboxylic acid. They're just showing you nitriles in nature. So they're usually pretty cytotoxic. And you got to be careful with HCN gas because it will bind to your hemoglobin and suffocate you. Also known to be in cigarettes. Okay, the Wittig reaction, and C is W, but it's actually pronounced Wittig. So you'll hear me say Wittig with a V, Wittig. This is actually a Nobel Prize winner. You'll see a lot of your Nobel Prize winners were carbon-carbon bond-forming reactions. So anytime you can do that, it helps make medicines and synthetic compounds. What's interesting here, you're taking an aldehyde or a ketone. Okay, so this is your functional group transformation to make an alkene. And you all know alkene reactions, you can do lots of different electrophilic addition reactions. This is like the only way you know to make an alkene that is not E1 or E2. And that's kind of nice because E1 or E2 comes from some kind of alkyl leaving group. But here we can convert an aldehyde or a ketone into an alkene. So this is very useful, and that's why the Wittig got a Nobel Prize. All right, so what is the Wittig reagent? You can actually order these, and so phosphorus, the phenyl are these groups here. Okay, so 3-phenyl, and then you have, okay, you can have any kinds of R groups, okay? So CH2, this is a double bond. See, carbon likes 4 bonds, right? Phosphorus likes 5 bonds. Okay, so phosphorus has 5 bonds, so there's the P3. And then here, this is just showing you the negative and the positive. This is your reagent, but here, the resonance structure would be, and I'll just make the phenyl, would be the positive on phosphorus and the negative on the carbon. So this makes a carbon anion, right? And that's a great nucleophile. And so here you have a ketone or aldehyde, so that's delta positive. You see that's a negative charge. So this is a strong nucleophile, so we don't need any acid catalyst to activate our electrophile. And then that's going to come here, But keep in mind that this oxygen is going to coordinate to phosphorus. So phosphorus loves oxygen, all right? So phosphorus is going to bond to the oxygen. Phosphorus loves the oxygen. They have affinity for one another. And once it binds, it's not going to let go. So your intermediate that you need to be able to draw, it's called an oxaphosphatane. Oxaphosphatane. It's actually one word. Oxaphosphatane. And it's a four-membered ring. And so here, your tetrahedral intermediate, right, oxygen, is going to bond to the phosphorus. So oxygen is going to bond to phosphorus. See, here's phosphorus. And phosphorus has its pH, pH, pH. And the phosphorus is still bonded to the carbon in your intermediate. So there's your carbon. The carbon's going to bond to the carbon. So carbon is going to bond to carbon. And the oxygen is going to bond to phosphorus. And it's going to make this four-membered oxaphosphatane. And then what happens is, I do want you to draw your oxaphosphatane. Then I want you to show the collapse to give you your alkene. So phosphorus is going to love the oxygen and it's going to take it. So those electrons are going to go to phosphorus, oxygen. And then these electrons, carbon and phosphorus, will break to make the double bond. And you'll see that in a prettier next slide. So here we have two carbons on the carbon, and you get a double bond there. And you see that phosphorus then takes the oxygen, and that's where the double bond comes from this bond here. So you can buy lots of different Wittig reagents. You can also make them. There's also this is an illid. Illid. Okay, so this is how you pronounce Y-L-I-D-E. Illid just means that there's a positive and negative charge adjacent to the atoms. The phosphorus is positive, the carbon is negative. And since they're right next to each other, that's called an illid. All right, so they're just showing you the resonance structures here where you get a double bond. And there's 10 electrons around phosphorus, which is 5 bonds. It can do expanded octet, and that's because of the d orbitals that are available to phosphorus. So these are stable and you can order them. This is showing you what if you had to make your own. What if you had to make your own illid? Well, then you would just do it an SN2 reaction with triphenylphosphine. So here's your illid. Now we have, we're making our illid here. I'm fine with you just like going straight to this compound. You could write this reagent if you needed to, double bonded CH2. And so I'm okay with you drawing that for your reagent. I do want you to be able to show your oxaphosphatane. I think I spelled it wrong in the previous slide. But you see this is a four-membered ring. The negative carbon is going to attack this carbon nucleophile, and then the oxygen electrons are going to go to the phosphorus, and that's how you get this four-membered ring, the oxaphosphatane, and then it collapses. So you have this carbon-oxygen bond is going to go here to make the phosphorus oxygen bond, and then you have the phosphorus carbon bond that's going to collapse to make the double bond of the alkene. One limitation that you get is you do get cis and trans. So you're going to get both stereoisomers. With the cis and trans are diastereomers. And you will get more cis than you, or trans, these are trans, E, than you get cis because trans are more thermodynamically stable. So, and they're showing you that this is used to the Wittig because you get lots of alternating double single bonds. It's used to synthetically make vitamin A. Okay, so if you get a compound like this is retrosynthesis. So remember we have these arrows here. And what would you want to do? You want to break that double bond. And then remember that the starting materials have to be either ketone or aldehyde. So I would choose this is your ketone because it's more carbon containing. And the reality is those two carbons here could probably, since you only have two carbons, you could probably purchase this. So what does that look like? CH3. And of course, if you were to draw a resonance structure of that, I'm just going to deliver the two carbons. So these are your two possibilities. This is the possibility I would probably choose just because you have less carbons for the Wittig. Um, yeah, so, and they're saying that this is a primary alkyl halide to make the Wittig is the preferred pathway. So, like I said, you more likely are able to get commercially available. Okay, so if you go to this transformation, you see that the oxygen here is a ketone and it gets replaced with a carbon-carbon alkene. So you need to add CH2. So this would be the reagent. 1, 2, 3, 4. This is one way you could do it, but you see how like you'd have to do the Grignard, and then you get a tertiary alcohol, and then you'd have to do an E1 where this gets protonated, and then you get your carbocation, and then that's your alpha, so then your beta hydrogen to do an E1 elimination. But you're also going to get the trisubstitute is going to be the Zatsevs is going to be your major product. That's going to be your minor product, so that's not great. But look at this, you can just add the Wittig reagent and this is your only product. I used to do this reaction quite frequently at Eli Lilly and it works well and I liked it. Okay, so what's the missing reagent here? You're making an alkene, so you can just do that. And then one of these has to be, this is a ketone, so there's your ketone, right? And then the other one has to be your Wittig. So would that be it? So 2 and 4. 2 and 4. All right, so if you're going to make amines, these are new functional groups. We talked about the amine. You have to have a mild acid because this is a weak nucleophile. So you're going to have to do lots of protonation steps. If it's a primary amine, it only has one R group on the nitrogen, one carbon. If it's a secondary amine, it's going to have 2 carbons on the nitrogen, and a tertiary amine is going to have 3. Because nitrogen likes 3 bonds and 1 lone pair, that's pretty much all you're going to get. And so what happens is you get protonation, and then you get the nucleophile adds, and then you get deprotonation to give you a carbonylamine. This is kind of like our hemiacetal. You're going to get protonation again, and then this lone pair will reform or will form a amine. And that an amine is a carbon-nitrogen double bond. It's also called a shift base. You see this a lot in biological reactions. Amine properties, they're sp2, so it's an sp2 nitrogen, so it's going to be planar, 120 degrees. And this amine formation has to be somewhat mild acid, acidic conditions of 4 to 5. That's why it can't be pH of 2, because then you're going to block this lone pair and you won't have a nucleophile. So that's why you need pH of 4 to 5. So this is the mechanism, and I don't agree with this mechanism, so make the correction. First thing you're going to do is get protonation. So you're going to get protonation because you have a weak nucleophile. So make that correction in your books, and then the amine now can come in and you get NHHR. Now it's a positive charge, so you're going to have the water the catalyst become an acid, and that is the carbenolamine. And then you do the next thing where you have to protonate it, the OH, and the, I agree with this, the lone pairs on the nitrogen will form the carbonyl, form the imine in this case because it's a nitrogen, and the OH leaves. OH2 leaves, and then you get deprotonation to get the imine. Now, primary amines is a primary amine because it only has one R group, forms imine. You're going to see where secondary amines will form an enamine. So just a different functional group. So so this one, what is the missing reagent? You need to recognize that this is an acetal. Remember, we did this in the first slide. So retrosynthesis, that carbon is, what you don't see there, what do you have here? You have 1, 2, 3. The hydrogen's not shown. All right, so that is an aldehyde. And then you add water. Okay, so we're going to add water. So this oxygen came from here, and then we're going to cut this here, and the hydrogen adds here. So you can see the acetal comes from this alcohol and this aldehyde. That's why you got to recognize that as an acetal. You have to have a little bit of acid because this is this alcohol is a weak nucleophile. So now let's look for it. This is your aldehyde. Make sure it has the right number of carbons. So that is 5, 6, 7. There's 7. And then we need to look for your alcohol. There it is. It's the diol. This is ethylene glycol. This is antifreeze. It's very poisonous and bad for you. And there's your acid. Amines in nature, you'll see this in your conjugated rhodopsin. So rhodopsin has a primary amine, and it will form a imine. This is an imine. See the nitrogen double bond? It will form an imine with retinal, which is an aldehyde. And that is synthesized by the rod cells in the eye. And this is showing you, so it forms this imine here, rhodopsin, that is rhodopsin, and then H nu is when light comes in, and the cis bond will isomerize to a trans. Now, keep in mind this has shape, okay? So this is like a door hinge. So think of this as like a door. You know how a door has shape and it can keep you from being able to go into one room or the other. And then when the H nu comes, this now goes from this shape to this shape, and it can turn on channels and open and close channels in your cells. formation of enamine. So this is going to be secondary amines. They react with aldehydes and ketones. So a secondary amine has 2 carbons and only 1 hydrogen. And so same thing happens. So if we look at this, let's take something like this one here, okay? So you take your ketone, and you're going to have mild acid, so you just go ahead and you got to protonate the carbonyl oxygen to activate it, to make it ready, a stronger electrophile. And now you have a secondary amine that will do nucleophilic attack to make your tetrahedral intermediate. And in this case, we have this, and I see it's protonated. So then we're going to regenerate our catalytic acid by deprotonate that, and that's going to make the carbonylamine. So that carbonylamine is kind of like your hemiacetal. Now, now we still have acid, and we want this OH to be a good leaving group. So we're going to protonate that. Now, at this point, we want to, we need to lose water. And so we're going to lose the OH here. You actually lose the alpha hydrogen. So it's this electrons that push here. And the reason why you lose that is because, so the water is because this alpha carbon is somewhat acidic. So I won't ask you to do this mechanism for the enamines. You need to know it for the amines and the acetals. But it is an enamine means that there's a carbon-carbon double bond, and then there's amine. So this is an amine, and this is a carbon-carbon double bond, so this is an N. So together, that functional group is an enamine. Okay, so this is showing you that you get nucleophilic attack. Like I said, I like to protonate that and get to the carbonylamine. So you are getting the lone pair coming in and opening that, but then water off. So this is, you were going to get reestablishment to be the enamine. Yeah, that makes sense because you want to have a neutral compound. Like I said, you don't need to know this mechanism. I will not ask you this mechanism for the enamine because we have not really talked about this alpha acidic proton. So, but make sure you can do the amine and the acetal, because these are good examples of weak nucleophiles. They're the only ones that you have. The other ones are strong, and you need a little bit of acid, and the mechanism is just a little bit more involved. The amine, you have a primary amine, so the nitrogen has 2 hydrogens. Acetal, methanol, or some kind of alcohol is your nucleophile. So they're just showing you here, if you have a primary amine, you're going to get an amine. If you have a secondary amine, you're going to get an N carbon-carbon double bond next door, and then amine. I do expect you to know, be able to draw an amine versus an enamine. This is just showing you that you can also, these are reversible reactions, so you can just add acid, and then you can see that this becomes the ketone, and then this adds hydrogen. So all of these, you're adding water to do the reversible. So the oxygen here is going to the carbon, and then your hydrogen is going to the nitrogen. So here, enamine, you're even adding water. So where you add in water, nitrogen is going to get one of these hydrogens. also the carbon is going to get a hydrogen, and then you're going to get the oxygen. So it's just the addition of water. Okay, so this is hydration of aldehydes and ketones. You can also add water. So a lot of times your acetone bottle, if you work in the lab, it will actually have some hydrate. I don't go through this. You can read this. I think you even have a POGIL question on it. Adding water to make a hydrate is uninteresting synthetically to me. So we're going to focus on when you're adding alcohols or primary amines with a little bit of acid catalyst. And so those are the ones we're going to focus on for the weak nucleophiles, not so much water. But they're showing you hydration levels, which is a little bit interesting. When you buy formaldehyde, 99.99% of the product is going to be the hydrate. So a lot of times you have to heat it and do some dehydration to actually get the formaldehyde carbonyl. It's masked. And the acetaldehyde, half of your product is going to be the hydrate because we have water in our atmosphere. Like I said, your acetone bottle is going to have some hydrate. And so free electron withdrawing groups, like I said, I'm not going to go into the hydrates, so you can read that on your own if you're interested. Same thing here. Not going to worry about the base catalyzed hydration. Once again, water is the nucleophile, not worried. Now this is what I do want to focus on, acetal formation. And to me this is very important because this has happened biologically. We use an acid called tosic acid. I told you about tosic acid. I drew the structure. It's an organic acid. These are not ethers. The acetals are the carbon, and C is bonded to an oxygen and oxygen. And the oxygen is bonded to carbons. Okay, this is the acetal. So the first thing you want to do is recognize that's an acetal. To go this way, you have to add water. Okay, so this carbon is going to get the oxygen, and these two, so it's an aldehyde or a ketone. You would think that this would be, there's also a thing called ketal, but it's just generically aka acetal, so it can be a ketone or an aldehyde, but a ketal would be more specific, but acetal is generally accepted as both a ketone starting material or an aldehyde. But notice the hydrogen on these oxygens come from the water. So tosic acid is the acid of choice because it's organic acid, and a lot of times you just do this in a solution of methanol, so you're definitely going to have two equivalents. You can assume that there's always going to be an excess, and then that's going to make an acetal. And so, but like you can go backwards by just adding lots of water. Okay, so ethylene glycol. This is antifreeze. It's actually very poisonous. That's why scientists a long time ago made it blue in hopes that people wouldn't drink it, especially kids. But then they made blue Gatorade, so it just kind of defeats the purpose here. But anyway, ethylene glycol, very toxic. Tosic acid, so this is going to get protonated. You can just do that with the protonation. Because this is a weak nucleophile, this is a great you're gonna find this is a protecting group, PG protecting group. This is going to add like so. And then you still have the OH here. And then you have the tosic acid catalyst that's going to deprotonate that. So do you see that that's a hemiacetal? The OH and then O. This is your hemiacetal. Now, the next thing that happens is you still got tosic acid. So now we're going to protonate the OH to make it a good leaving group. And you'll see these in the future slides here. you still have this intramolecular nucleophile. So then the nucleophile is going to, well, this carbon is, you're going to reform the carbonyl, and that's going to leave. This is the same mechanism. Okay, so now you get another nucleophilic attack, and it's going to attack the activated carbonyl. Here. And then tosic acid is going to regenerate the acid by deprotonating. And that's how you get the cyclic acetal. You can go forward or backwards, driven by Le Chantelier's principle. Basically, you use this thing called a Dean Stark trap, and it can, named after Dean Stark, it can collect the water. And if you pull the water away, you see how water is on the product. If you remove the water, then you're going to drive the equilibrium, Le Chatelier's principle, towards the cyclic acetal. So if you wanted to drive it the other way, you just add water and acid, and then you're going to get your alcohol and your ketone. And you do need to be able to go forward and backwards with the reagent. So this is showing you how to form the hemiacetal mechanism. You protonate the carbonyl oxygen, and then the nucleophile attacks, and then you have to deprotonate the alcohol to get you the hemiacetal. Then to go to the acetal, you take this hemiacetal, you got to protonate the OH to make it a good leaving group. This is what I want to see. I want to see that I don't care if you show the resonance, but I want to show that I want to see this. I want you to do this at the same time where you reform the carbonyl. This is very important because this is nucleophilic acyl substitution. And then another molecule of the alcohol will attack that activated carbonyl, and then you get deprotonation of the nucleophile to give you an acetal. An acetal is a new functional group. Now, if you have an acetal, you need to be able to hydrolyze it back to the starting material. And the starting material, you need to recognize you're adding water, okay? So this carbon is going to get the oxygen to make the carbonyl, and then the oxygens here are going to get the hydrogens. And so there's two of them. Here, this is your acetal, and this is where the water will add to the oxygens. So you can see that here, ethylene glycol, and then the oxygen adds to that carbon here. So there's your water. And so it's a protecting group. So if you need to ever hide, or same thing, aka protect, a carbonyl, an aldehyde or a ketone, from reacting in a reaction, you can do this reaction here with just this and some acid, and now you have an acetal, and this will not react. So then you can go on with all your steps of synthetic reactions, and then you can add acid and water, and then you can get back your ketone. So protecting groups, that's the mentality. Here you have a ketone and you have an ester. I told you ketones are lots more reactive. What if you don't want it to react? If you try to do lithium aluminum hydride here, okay, and this is what you want. You want the ketone, but you want the carboxylic acid to be reduced to the alcohol. Well, unfortunately, you're going to get the ketone reduced first. but you can shut that down. If you do a step first, and you react it with some para-toluene sulfonic acid and ethylene glycol, then what you would get is the ester is not going to do anything, and then this is ketone is going to make the acetal here. 2, 3, 4, 5, 6. And then you can react it with lithium aluminum hydride, which is 1, and then water. A lot of times you can add H2O and H3O plus, and you're quenching the lithium aluminum hydride, and that will give it back. If you just do lithium aluminum hydride, you're going to get 1, 2, 3, 4, 5, 6, the reduction of the primary alcohol, and then the acid in the water is going to hydrolyze this back to the acetal. So the acid, the water is going to add here. We don't care about this. This is just, but this carbonyl here gets the oxygen. 1, 2, 3, 4, 5, 6. And so that's how you can get the desired reduction. So that's what they're showing you here. The first step you're going to have to do is protect this. So you're going to need ethylene glycol and tosic acid to protect the aldehyde, the ketone. The ketone as an acetal that protects it. And then you can do lithium aluminum hydride and water that reduces an ester to the primary alcohol. And then you can deprotect with acid and water to hydrolyze that ketone back to the carbonyl to give you your desired major organic product. So cyclic acetals, these are quite interesting. They give 5 or 6 membered rings. And these are stable compounds that you, hemiacetals here, that are stable. So here, how do you get that? You would have to have an intramolecular nucleophile here. So this will, a little bit of acid, this gets protonated, right? One, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. And now you have this intramolecular nucleophile. And that's how you get, so a lot of these are stabilized by an intramolecular reaction. Notice this is 1, 2, 3, 4, 5 carbons away. Okay, here this is 1, 2, 3, 4, and there's less for the 4. Now, do you recognize these compound structures? Do you recognize them? How about, do you know your DNA structure? Have you ever seen the structure of like DNA? You got some kind of nitrogen base, right? And you got your phosphates. DNA, deoxyribose, okay? So you see how this is a 1, 2, 3, 4, 5 membered ring. 1, 2, 3, 4, 5. So then you could have nitrogen there. You also, the sugars. What about glucose? Have you ever looked at your structure of glucose? And then maybe it reacts with another polymer of glucose. Have you ever seen some of your sugar molecules here? Okay, so look at here. This it's called a glycosidic bond. And it is a, in this case, it's a 2, 3, an acetal. If you just have one sugar, it's a hemiacetal. And glucose, and glucose is actually the cyclic form is what travels in your blood. Okay, so the cyclic form is in the blood, and it is a hemiacetal. So these are kind of important biologically. And so this is just showing the mechanism for the intramolecular nucleophilic attack of an alcohol to give you the hemiacetal. You do have a new stereogenic center, and it's for our purposes, it will add from the top and the bottom, so you'll get enantiomers. So you can just draw that here in your glucose. A lot of times you'll see the alpha linkage where the OH is down, or the beta, and we'll see some slides on. This is a hemiacetal. Now this is a new functional group, so it reacts a little different. You can add some acid and methanol, and if you ever do sugar chemistry and you do reactions on sugars, this is a very important reaction because you can add acid and methanol, and only this acetal glycosidic bond will react, and it's because it's an acetal, so you can protect that as an acetal. And that's just showing you. So this is a hemiacetal, and then you protonate first. We reform the carbonyl, so I want to see these two here, and then just go straight to here, and then your nucleophile will attack here to give you this, and then you deprotonate to get you an acetal. So here, if you added methanol and acid, this is the only carbon that's going to react because this is a hemiacetal. This is just a regular old alcohol. Okay, regular old alcohols are not going to do anything here. So I told you that carbohydrates are acetals. So you see that this carbon here is a hemiacetal. And this would be a beta. Alpha would be when the OH is down. This is equatorial up. Glucose has all its OHs in the equatorial positions. So if you ever had to do the cyclic structure of glucose, all the OHs are equatorial. So here's lactose. This is an acetal now. You see how it's a disaccharide, and the carbon there is an acetal. So here they're showing you how this happens. This is this here is equatorial. This is your hemiacetal, and it could go alpha beta in the open chain, and it is about 1% of the time in the open chain. You have an aldehyde. This is an aldehyde. So the OH does an intramolecular nucleophilic attack to make the hemiacetal. So like I said, if this is a hemiacetal, you can break that there and see that that's an OH, and that's a carbonyl. All right, so what is the major product? I expect you to be able to do functional group transformations. I hope that you can see that this is an aldehyde. This is a strong nucleophile. And not only is it a strong nucleophile, it is a Wittig reaction. So hopefully you're thinking functional group alkenes before you even look at any of the options. And you kind of just talk to yourself and see what you know. And so this is going to be 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then on this carbon, the double bond oxygen carbon is going to get replaced with these 3 carbons here. So, and then count your carbons. 1, 2, 3, 4, 5. 5 carbons here, 3 carbons here. 5 plus 3 is 8 carbons. And so let's make sure we have that. We have 1, 2, 3, 4, 5, 6, 7, 8. And here, not an alcohol, not a ketone, so we got it down to 2. and count your carbons. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So we do have the same number of carbons. This is a tri-substituted alkene. This is tri. This is di. So if you do your classifications, it's easy to narrow that down, and then you can see that they do match here. Okay, so you do need to know your priorities. An aldehyde will have a higher priority over an alcohol, but we still got to get it in the whole long chain, but we're going to count from right to left. 5 is pentane. We're going to drop the E and add al. We don't need to write pentanal. We don't need to specify that that's on number 1. We do have an OH though on number 4, and so that's pentan, and then we want for all, and then al. Let's see, we have the al here, so and so here, that's one way. This is named as a substituent for hydroxy pentanal, so this is your best name. Okay, so thionyl chloride, we got carboxylic acid. This is nucleophilic acyl substitution, and it makes an acid chloride. So that is it. Thionyl chloride makes an acid chloride. 1, 2, 3, 4 carbons. Count your carbons, 4 carbons. B is your answer. So you need to know these functional group transformations and the reagents that are required to do those. And that concludes this chapter.